Steel is weird. Copper, I'm going to draw copper and aluminium in roughly to scale. Let's take that down. Let's say the yield strength of mild steel is 250. Right now I'm only looking at elastic behaviour. This is reversible. If I take that force off, it goes back to zero. So, Young's modulus. Steel has a particular Young's modulus. Copper does not follow a straight line relationship per se. It is progressively yielding. Steel, as you know, has a double yield point. That's when all the carbon atoms let go from the interstitial positions. That's why steel you get that double yield point behaviour, the upper and the lower yield point. Copper you do not. Aluminium you do not. That double yield point, I made a mistake earlier, I'm cutting back and editing this in. That only exists in annealed steel. Once the steel is work hardened, it does not have a double yield point. It only exists in annealed steel. What it is, that's the point where the atoms are all in perfect position and the only thing stopping them moving is the carbon atoms sitting between them. Once those carbon atoms let go, that's when you get the upper and the lower yield points. Once you've already displaced the atoms from their uniform position or their equilibrium position by work hardening it, then the carbon atoms are already displaced and you don't get that double yield point. Body-centered cubic metals have that. Face-centered cubic metals, which is 90% of all the metals available, don't have a double yield point. Steel is weird. Copper does that. Aluminium, I'm drawing these to scale. Starts out at about that angle. It has a different spring constant. If you think about that spring constant as being the restoring force of the spring, what we have here in steel is I've got two iron atoms. Looking at it at atomic scale that are bound by atomic force of particular strength. I've drawn it as a spring, but of course it's a chemical attraction. Copper, that chemical attraction's different. Aluminium, that interatomic attraction, I'll say interatomic, not chemical, that interatomic restoring force is different. So the further apart you move an aluminium atom, you need less force to move aluminium than you do copper, a set amount. You need less force on copper than you do on steel. That's basically Young's modulus. For steel, Young's modulus is easy. Young's modulus is just that. The slope of that line. It also equals similar triangles. Identical triangles, what's the mathematical term? Similar triangles?
Similar triangles.
Similar triangles. All those three triangles have the same slope. That angle in there is the same. The slope of that triangle is the same. Let's have a look at copper. Is that triangle there? Is it there? Is it there? It's progressive yield, but I'm going to say that's about the angle it starts at. The slope of this line is called Young's modulus. Instead of the spring modulus, we have got Young's modulus, which is the elastic modulus of the material. Behaves exactly the same way. So, you don't need to know these numbers for the exam. Steel is 200. Gigapascals. Aluminium is 70 gigapascals. Copper is 140 gigapascals. And notice the slope of those lines. 1, 2, 3. 70, 140 is twice as much, 200 is close enough to 210. So we've got three different slopes there. That's essentially elastic behaviour of metals.